Graphs have many important features. This video I'm going to look at what the area on the graph represents. Okay, here we have an acceleration time graph. What does the area on this graph represent? So we can obtain the area by doing the acceleration times the change in time. So we look for an equation which links these two. So the equation is the definition of acceleration, which is the rate of change of velocity over change in velocity over change in time. If we rearrange this to get acceleration times change in time, we see that that represents the change in velocity. So the area under this graph represents change in velocity. Okay, here we have a velocity time graph. The area can be determined by doing velocity times change in time. What's the equation that links these two together? It's the definition of velocity, which is rate of change of displacement, or change of displacement over change in time. And if we rearrange this, we get the area on the graph represents the change in displacement. Now you can see here this is positive area, and underneath here that's negative. So the one area above the x-axis represents positive displacement, while the area below is negative displacement, which you need to subtract. Okay, we have a current time graph here, and the area can be determined by doing current times change in time. The equation that links these two is the definition of current, which is a rate of flow of charge or change in charge over change in time. Rearranging this, we get that the area on the graph represents charge. Okay, force time graph here. So the area is force times change in time. The definition we're looking for here, which is force times change in time, is change in momentum, or sometimes called impulse. Okay, here we have a force extension graph, extension of a spring. But the truth is this can be any force distance as long as that distance is parallel to the force. The definition that we're looking for here is the definition of work done, which is force times distance moved parallel to the force. So you can see the area on this graph represents work done. In the case of a spring, it's the elastic potential energy stored in that spring. Okay, here we have a power time graph. Power is a rate of change of energy, or rate of change of work done if you want. Rearrange this equation, we get the area on the graph represents the energy or work done. Okay, slightly harder question here. Show that the area on the stress strain graph represents the energy stored per unit volume. Okay. So firstly, when you stretch a string or a wire by applying a certain force F, its change in length is delta L, its original length is L, and its cross-section area is A. Okay, so to get the area in the graph, we'll have to do the y-axis times the x-axis, or normally change in x-axis. But here we can just do area in the graph is stress times strain. Stress is force over area. Strain is change in length over length. So if we bring these two together, you can see that the top here, force times change in length, that is actually work done, or energy stored. And the bottom, for area times length, cross-section times length, is actually volume. Okay, so that's basically work done over volume. Okay, the graph shows how the gravitational field strength varies with distance from the center of a planet. What does the area on the graph represent? The area on the graph can be determined by doing gravitational field strength times change in distance. Now what's the equation which links these? There's many equations for gravitational field strength, but the one that links these two together is gravitational field strength equals minus the change in potential, gravitational potential over change in distance. Rearranging this, I'm ignoring the negative sign, it doesn't matter for now. We can see that the area on the graph represents a change in gravitational potential. Okay, exactly the same for electric field strength. The area underneath the electric field strength over distance graph represents the change in electric potential. Okay, here's a graph from the magnetic fields topic. We have the EMF induced against time as a magnet falls through it. So the equation that links EMF and change in time is the Faraday's law, which is EMF is directly proportional to the rate of change of flux linkage. So rearranging this and ignoring the negative sign for now, we get the area on the graph represents that change in flux linkage.